Right now, in the silence of space, something is holding our entire galaxy together. An invisible monster so immense that 4 million suns couldn't match its mass. Tonight we'll discover just how big Sagittarius A truly is. Where are you listening from right now? Whether you're settling in for the night or simply pausing to listen, you're welcome here. If this calm finds you and you enjoy these gentle journeys through the cosmos, feel free to stay a little longer, leave a quiet, subscribe, a soft like, or simply let the stillness settle in. Let's begin. For centuries, humanity has gazed toward the center of the night sky and seen only darkness. Even the most powerful optical telescopes could not pierce the dense veils of interstellar dust that stretch across the galactic plane. The core of the Milky Way remained hidden like a candle burning behind a thick curtain. To ancient astronomers, the band of light we call the Milky Way appeared eternal and unchanging, a river of stars flowing across the heavens. Yet beneath that shimmering arc in the constellation of Sagittarius, something colossal waited patiently to be discovered. Here lies a profound paradox. The brightest region of our galaxy, the place where stars crowd most densely, where gravity concentrates most powerfully, appears to us as the darkest. How can the galactic center, teeming with billions of suns, look like an empty void? The answer lies not in absence, but in obstruction. Between us and the heart of the Milky Way stretch vast curtains of cosmic dust and gas. These clouds, spanning thousands of light years, absorb and scatter visible light. They act like fog, rolling across a landscape, obscuring everything beyond. The center burns brightly, but its light cannot reach our eyes. We are blind, not because there is nothing to see, but because something stands in the way. For generations, astronomers stared into this darkness and wondered, what could possibly hide behind such a veil? The question seemed unanswerable. Optical telescopes, no matter how large or sophisticated, could not penetrate the dust. The galactic core remained a mystery, tantalizingly close, yet utterly unreachable. Then came a breakthrough. In the mid-20th century, astronomers began building radio telescopes, instruments that do not look at the universe, but listen to it. Radio waves with their long wavelengths slip through interstellar dust like whispers through walls. What visible light cannot penetrate radio waves, pass through effortlessly? In the 1970s, radio astronomers turned their instruments toward the constellation Sagittarius, and there, hidden behind the cosmic fog, they detected something extraordinary. A compact source of radio energy, brighter than anything else in the galactic center, pulsed steadily from a single point in space. It was not a star, it was not a cluster, it was something entirely unknown. They named it Sagittarius A star, marking it with an asterisk to denote its unusual nature. The symbol was not decorative, it was a flag, a signal that this object demanded special attention. Here was something that screamed in radio frequencies while remaining utterly silent in visible light. What kind of object could behave this way? What could generate such immense radio energy while staying invisible to every optical telescope on Earth? The question hung in the air, unanswered, but impossible to ignore. Whatever lay at the galactic center was not ordinary. It was something far stranger, something that hinted at physics operating at the most extreme limits. The radio emissions told a story of violence, of matter accelerating to near light speed, of magnetic fields twisted into knots, of gravity so intense that space itself might be warping, but the details remained hidden, shrouded behind the same dust that had concealed this mystery for so long. Sometimes the most important things in life are invisible. We do not see love, but we feel its warmth. We do not see gravity, but we witness its pull. We do not see the wind, but we watch the trees bend. And at the center of our galaxy, hidden behind curtains of dust, something vast and powerful had been shaping the destiny of billions of stars long before humanity ever looked up and wondered. The veil was beginning to lift. The invisible was about to become known. But discovering that something exists is only the first step. The harder question remained: if we cannot see it, how do we measure it? How do we weigh something made entirely of darkness? How do you measure something you cannot see? How do you weigh a ghost? This was not a philosophical question for astronomers studying the galactic center. It was a practical challenge, demanding a clever solution. The answer, as it turned out, lay not in observing the invisible object itself, but in watching the way it moved everything around it. Near the galactic core, certain stars behave strangely. Their movements caught the attention of astronomers equipped with powerful infrared telescopes, instruments capable of seeing through the dust that blocks visible light. These stars did not drift lazily through space. Instead, they raced across the darkness, like trapped fireflies tracing long elliptical paths around an apparently empty point in space. Something invisible was pulling them, controlling their motion with an iron grip. To see these orbits required extraordinary patience. Teams of astronomers returned year after year, capturing images of the same stars and measuring their positions with painstaking precision. Slowly, over decades, the truth emerged. These stars were not wandering, they were bound. All of them circled the exact same point, like planets around an invisible sun. One star became the key witness, S2. This bright blue giant, roughly 15 times the mass of our sun, completes a full orbit around the galactic center every 16 years. Consider what that means. Our sun takes 240 million years to orbit the galaxy once. S2 completes its journey in the span between a child's birth and their high school graduation. At its closest approach, S2 sweeps to within just 120 astronomical units of the center and accelerates to 17 million miles per hour. That speed defies imagination. The Voyager spacecraft, humanity's fastest envoy to the stars, travels at 38,000 miles per hour. S2 moves 450 times faster. It could cross the distance from Earth to the Moon in less than 90 seconds. This extraordinary speed became a cosmic scale. Newton's laws of gravitation, refined by Einstein's general relativity, provide a simple relationship. If you know how fast something orbits and how far away it travels, you can calculate the mass of what it orbits. The mathematics is straightforward. The implications are staggering. Astronomers measured S2's velocity with exquisite care. They tracked its position night after night, year after year, building a complete map of its elliptical path. Then they performed the calculation. The result left no room for doubt. The invisible anchor at the galactic center weighs 4,297,000 times the mass of our sun. The uncertainty in this measurement is just 12,000 solar masses. In astronomical terms, that precision is breathtaking, like weighing an ocean and knowing its mass to within a single swimming pool. But S2 revealed more than just a number. Its orbit also eliminated alternative explanations. If the center contained a dense cluster of stars, rather than a single object, their combined gravity would disturb S2's path over time. The orbit would wobble. It would precess unpredictably. It would change. Yet decade after decade, S2 traced the same perfect ellipse. This unwavering stability proved the mass was not scattered among many objects. It was concentrated in one. No ordinary star could exist at such density. No cluster could remain so perfectly unified. Only one possibility explained the evidence: a supermassive black hole. 4 million suns, crushed into darkness, compressed into a region smaller than our solar system, creating a gravitational well so deep that not even light escapes. There are things we cannot see, cannot touch, cannot measure directly, yet we know they exist by the traces they leave behind. Love is known by its warmth. Trust is known by its actions. Gravity is known by the way objects fall. And the monster at our galaxy's heart is known by the way it moves stars, a cosmic dance, revealing an invisible partner that has shaped our galactic home since long before humans ever wondered what lay beyond the night sky. The stars had revealed the mass, but mass alone tells only part of the story. To truly understand this darkness, we needed to witness something even stranger, the way it bends, not just the paths of stars, but the very fabric of space and time itself. Near the galactic center, the night sky looks nothing like the calm darkness we see from Earth. Stars do not drift lazily through space as they do in our quiet neighborhood. Instead, they race, they plunge, they whip around invisible anchors at speeds that defy comprehension. This is not the gentle waltz of distant constellations, it is a cosmic sprint, a frantic ballet performed in absolute darkness. Imagine standing near the galactic core. If such a thing were possible, the sky would blaze with thousands of stars crowded so closely together that true night would never fall. And among these stellar multitudes, you would witness something extraordinary: stars tracing elegant arcs across the heavens, all circling the same empty point in space. Each star follows its own path, its own ellipse, like dancers moving to music only they can hear. These are not random wanderings. Each orbit is precise, governed by the invisible conductor at the center. The stars move as if choreographed, as if guided by laws written into the fabric of the universe itself. And in a sense, they are. Gravity provides the rhythm, space-time provides the stage, and the stars, unable to resist, unable to escape, perform their eternal dance. Among these stellar dancers, SN2 takes center stage. Every 16 years, this bright blue giant completes one full revolution around the galactic center. Its orbit is not a circle, but a long-stretched ellipse, narrow at one end, wide at the other. This shape tells a story of extremes. At its farthest point, S2 drifts slowly, almost leisurely, as if pausing to rest before the next plunge. Here, thousands of astronomical units from the center the black hole's pull weakens just enough for the star to catch its breath. It glides through space like a ship coasting on calm seas, its motion steady and unhurried. But then comes the turn. Slowly at first, then, with gathering momentum, S2 begins its descent back toward the center. The invisible anchor pulls harder. The star accelerates. What began as a gentle drift becomes a rush, then a plunge, and finally, an all-out sprint. At its closest approach, S2 screams past the galactic center at 17 million miles per hour. It skims within 120 astronomical units of the black hole, close enough to feel the full fury of its gravitational grip. For a brief moment, measured in days rather than years, S2 becomes the fastest moving star we have ever observed. Then just as quickly, it begins climbing back, out momentum, carrying it away from the abyss. This is not chaos, it is precision. Year after year, orbit after orbit, S2 traces the exact same path. No wobble, no drift, no deviation. The ellipse remains perfect, as if drawn by an invisible hand. Astronomers tracking S2 across decades have watched it complete multiple orbits, and each time the star returns to the same positions with clockwork accuracy. This perfection is itself a marvel. If the galactic center contained a cluster of objects rather than a single mass, their combined gravitational tugs would disturb S2's orbit over time. The path would shift. It would precess unpredictably. It would change. But it does not. The orbit remains flawless, pointing unambiguously to a single unified source of gravity. Yet the dance holds one more secret, one more layer of strangeness. S2's orbit does not quite close on itself. With each revolution, the entire ellipse rotates slightly, shifting its orientation in space. Over centuries, this rotation traces a pattern, like the petals of a flower, slowly opening one revolution at a time. Each orbit is a petal. Each century is a breath. This effect, called orbital precession, was first noticed with Mercury in our own solar system. Einstein's general relativity predicted it in regions where space-time curves, sharply orbits, do not repeat perfectly. They drift. They rotate. They draw rosettes instead of simple ellipses. For S2, the precession is unmistakable. The star's path shifts by a small but measurable amount with each orbit, exactly as Einstein's equations predict. This is not merely interesting, it is proof. Proof that space-time itself bends near massive objects. Proof that gravity is not simply a force pulling through empty space, but the curvature of space and time themselves. The dance, then, is more than beautiful. It is evidence. Every loop, S2 traces every petal. It draws in. The darkness confirms a theory written a century ago by a man who never saw these stars, never witnessed their motion, but understood the mathematics of the universe deeply enough to predict what they would do. Other stars join the dance. S62 orbits even closer, completing its circuit in just under 10 years. S474 holds the record for the closest approach, diving to within a handful of astronomical units of the event horizon itself. Each star adds its own thread to the tapestry, its own voice to the cosmic symphony. And all of them, S2, S62, S4704, and dozens more, paint the same picture. They reveal an invisible partner at the center of the dance floor, a presence so massive and so compact that it can only be one thing: a supermassive black hole, silent and unseen, conducting the ballet with nothing but the pure force of its gravity. In the darkness, stars draw flowers with light. Each orbit is a petal unfolding. Each passage is a brushstroke in a painting that takes centuries to complete. The black hole does not announce itself with brilliance or sound. It announces itself through motion, through the graceful arcs of stars held captive in its grip. This is the beauty, hidden in chaos. This is the order underlying what seems like frenzy. And this is how we came to know with absolute certainty that at the heart of our galaxy sits not a cluster, not a cloud, but a singular darkness around which everything, including us, eternally revolves. The stars had shown us the dance, but there was something stranger still waiting to be discovered. Not just how the black hole moves stars through space, but how it bends something even more fundamental: time itself. We grow up believing that time is universal. A second on Earth is a second on Mars, a second in the farthest reaches of the galaxy. Clocks everywhere tick at the same steady pace, marking the passage of moments in perfect synchrony. This intuition feels so obvious, so deeply embedded in our experience that questioning it seems absurd. But it is wrong. Time does not flow uniformly across the universe. It bends, it stretches, it slows. And nowhere is this strange truth more evident than near the monster at the center of our galaxy. Albert Einstein understood this more than a century ago. His theory of general relativity made a radical prediction: time runs more slowly in strong gravitational fields. The stronger the gravity, the slower the clock. Near a black hole, where gravity reaches its most extreme expression, time itself begins to falter. For decades, this remained theoretical. Einstein's equations said it must be true, but observing the effect directly seemed impossible. Black holes were too distant, their environments too chaotic, their influence too subtle to measure from 26,000 light years away. Then came S2, the same star whose orbit revealed the black hole's mass, became the key to testing Einstein's strangest prediction. In 2018, as S2 made its closest approach to Sagittarius, star, astronomers watched with instruments sensitive enough to detect the tiniest shifts in the star's light. They found exactly what Einstein had predicted. The light arriving from S2 was shifted toward the red end of the spectrum. This was not the ordinary Doppler shift caused by motion, though S2 was indeed racing at 17 million miles per hour. This was something deeper, something stranger. This was gravitational redshift, the signature of time itself, running more slowly near the black hole. Here is what was happening. As S2 skimmed close to the event horizon, the black hole's gravity pulled not just on the star's mass, but on the photons, the particles of light streaming away from its surface. Each photon had to climb out of the gravitational well, and in doing so, it lost energy. Since light cannot slow down, it always travels at the same speed. The only way for photons to lose energy is to change color, shifting from blue toward red. But this redshift reveals something profound about time. When light loses energy, climbing out of a gravitational field, it is not just the light that changes, it is time itself. Clocks near the black hole tick more slowly than clocks far away. Seconds stretch, minutes elongate, time becomes elastic. Imagine this thought experiment. You carry an atomic clock, the most precise timekeeper humanity has ever built, and somehow manage to fly it close to Sagittarius A star. From your perspective, riding alongside the clock, nothing seems unusual. The clock ticks normally. Each second feels like every other second. You notice no difference. But back on Earth, observers watching your journey through powerful telescopes would see something entirely different. To them, your clock would begin ticking more slowly. The intervals between each tick would grow longer. As you approached the event horizon, the effect would become extreme. Your clock would slow to a crawl each second, stretching into minutes, then hours, then years. If you could somehow hover at the very edge of the event horizon and then return to Earth, you would find that far more time had passed here than you experienced. Days for you might equal decades for Earth. Months for you could span centuries back home. This is not science fiction. This is the mathematics of general relativity confirmed by observation. The paradox is, both perspectives are correct. To you near the black hole, time flows normally. To distant observers, your time appears frozen. There is no contradiction because time itself is not absolute. It is relative to the observer's position in the gravitational field. This effect is not limited to black holes. We experience it every day, though on scales too small to notice directly. Time runs slightly faster on mountaintops than in valleys. Time runs faster for satellites orbiting Earth than for people on the ground. The difference is minuscule, nanoseconds per day, but it is real and measurable. In fact, the global positioning system relies on correcting for this effect. GPS satellites orbit high above Earth, where time runs slightly faster than on the surface. If engineers did not account for this time dilation, the system would accumulate errors of several kilometers per day. Every time you use GPS navigation, you are depending on Einstein's theory of relativity to function correctly. But near Sagittarius A star, the effect is no longer subtle. Time does not just run slightly slower, it crawls. At the event horizon itself, time appears to stop completely for outside observers. Anything falling in would seem to freeze at the edge, dimming and reddening as its light stretches infinitely until it fades from view altogether. Yet, from the perspective of the falling object, nothing special happens at the horizon. It crosses smoothly, continuing inward, experiencing time normally even as the outside universe ages and evolves beyond recognition. Time, then, is not the steady river we imagine. It is not a universal clock ticking uniformly across the cosmos. It is something far stranger, a dimension woven into the fabric of space-time, capable of bending, stretching, and slowing wherever mass curves the universe around it. The observation of S2's gravitational redshift was more than a confirmation of Einstein's theory. It was a glimpse into the fundamental strangeness of reality. Time is not fixed. It is not constant. Each of us lives in our own personal flow of time, shaped by our position in the gravitational landscape of the universe. Near Sagittarius, a star time moves to a different rhythm. The stars racing past it experience fleeting moments, while the galaxy beyond ages eons. And in this bending of time, in this warping of the most basic dimension of existence, we see the true power of the invisible monster at our galaxy's heart, a power that extends beyond space, beyond matter, into time itself. We had seen the stars dance. We had witnessed time bend. But the ultimate proof still awaited a photograph of the unphotographable, an image of darkness itself. For decades, the idea of photographing a black hole seemed absurd. How do you capture an image of something that, by its very nature, emits no light? A black hole is defined by what it does not do. It does not shine, does not glow, does not send any signal back to the universe. It swallows everything, including the photons that would allow us to see it. Photographing a black hole would be like trying to photograph the absence of something, like capturing a picture of silence or stillness. Yet astronomers refused to accept impossibility. If you cannot photograph the object itself, they reasoned, perhaps you can photograph its shadow. Every black hole, no matter how dark, sits against a backdrop of glowing matter. Gas and dust spiral around it, heated to millions of degrees, blazing with radiation. Against this luminous stage, the black hole should cast a shadow, a perfect silhouette, where no light can exist, surrounded by a ring of brilliance, bent and magnified by gravity itself. This was the idea, but turning it into reality would require solving problems that seemed insurmountable. The first challenge was scale. Sagittarius A star, for all its immense mass, appears incredibly small from Earth. Imagine placing an orange on the surface of the moon and trying to photograph it from your backyard. That is roughly the angular size of the black hole's shadow, as seen from our planet. It spans just 50 micro-arcseconds across the sky, a measurement so tiny it defies ordinary comprehension. To resolve such fine detail requires a telescope of extraordinary size, not merely large, enormous. The resolution needed would demand a telescope effectively as wide as the entire Earth. Of course, no such instrument could ever be built. No single mirror or lens could span continents and oceans. The engineering would be impossible, the cost unthinkable. But what if you did not build one giant telescope? What if instead you linked many smaller telescopes together, scattered across the globe, and synchronized them to work as one? This concept, called very long baseline interferometry, allows radio dishes separated by thousands of kilometers to function as a single planet-sized eye. This was the solution. This was the Event Horizon Telescope. Over several years, a collaboration of more than 300 scientists from dozens of institutions across multiple continents came together to attempt the impossible. They identified 8 radio observatories spread from Hawaii to Chile, from Arizona to the South Pole, from Spain to Mexico. Each observatory would point towards Sagittarius A star, simultaneously recording radio waves from the black hole's glowing surroundings. Together, their combined observations would create the resolving power of a telescope as wide as Earth itself. But coordinating such a project required precision beyond anything attempted before. Every telescope had to observe at exactly the same moment. To synchronize their clocks, astronomers used atomic timepieces accurate to within billionths of a second. Even the smallest timing error would blur the final image beyond recognition. Weather posed another obstacle. All 8 observatories had to have clear skies simultaneously, an event rare enough to require careful planning and patient waiting. If clouds covered even one site, the entire observation would lose crucial data. Teams monitored weather patterns across the globe, looking for windows of opportunity when the atmospheric conditions aligned. Then came the observations themselves. Over several nights in April 2017, the telescopes turned toward the galactic center. They did not capture ordinary photographs. Instead, they recorded raw radio data, petabytes of information, far too much to transmit over the internet. The data filled hundreds of hard drives, each one physically shipped to central processing facilities. Some drives traveled by plane, others were carried across borders by hand. One shipment from the South Pole had to wait months for winter to end before anyone could retrieve it. Once the data arrived, the real work began. Supercomputers at the Max Planck Institute in Germany and the Haystack Observatory in Massachusetts began processing the signals. The task was staggering. Imagine collecting recordings from 8 different cameras pointed at the same scene, each camera slightly out of focus and capturing different wavelengths. Then imagine trying to combine those recordings into a single clear image, correcting for Earth's rotation, atmospheric distortion, and the motion of the telescopes themselves. The computers ran for years. Scientists tested thousands of different algorithms, comparing results, searching for patterns, looking for consistency across multiple independent analysis methods. Slowly, painstakingly, an image began to emerge from the noise. What they found matched Einstein's predictions with eerie precision. In May 2022, the world saw the result. The Event Horizon Telescope released the first direct image of Sagittarius A star, the black hole at the center of our own galaxy. There it was, exactly as theory had foretold, a glowing ring of turbulent plasma blazing with energy bent into a near-perfect circle by the warping of space-time. And at the center, surrounded by that luminous halo, sat a region of absolute darkness. That darkness was the shadow of the event horizon itself. Not the event horizon. Directly light from the horizon can never reach us, but its projection magnified by the bending of space around it. The shadow appeared larger than the black hole's true size, stretched and distorted by gravity into a circle roughly 2.5 times wider than the event horizon. The glowing ring surrounding the shadow was no ordinary light. It came from plasma, spiraling around the black hole at nearly the speed of light, particles colliding and radiating as they plunged toward oblivion. Some of this light came from material behind the black hole, bent around its edges by gravity until it appeared to glow in front. This gravitational lensing created the perfect ring, a cosmic magnifying glass revealing the monster lurking within. The image was blurry, turbulent, unstable. Sagittarius. A star flickers and changes on timescales of minutes, making it far harder to photograph than the steadier black hole in galaxy M87 that had been imaged 3 years earlier. But even through the turbulence, the fundamental shape was unmistakable. A ring of light, a shadow of darkness, exactly as Einstein had predicted in 1915, more than a century before anyone could hope to test his theory with such precision. This was more than a photograph. It was vindication. For decades, general relativity had been tested in laboratories, with satellites, through observations of planetary orbits and the bending of starlight. But this was different. This was a direct visual confirmation of Einstein's most extreme prediction that space-time itself could curve so sharply that it would trap light forever, creating a boundary between existence and oblivion. The image represented something else as well, a triumph of human cooperation. Scientists from dozens of countries speaking different languages, working in different time zones, believing in different philosophies and religions, had come together for a single purpose. They had combined their instruments, their expertise, their data, and their dreams. They had synchronized their efforts across continents and coordinated their work across cultures. No single nation could have achieved this. No individual observatory, possessed the resolution required. The telescope that captured this image was not built in one place. It was assembled from fragments scattered across the entire planet, unified by nothing but shared curiosity and collective determination. In a world often divided by borders and beliefs, by politics and prejudice, this project stood as a reminder of what we can accomplish when we work together. The photograph was not just of a black hole, it was a portrait of human potential, a testament to what becomes possible when we point our instruments and our intentions in the same direction. And so, after a journey spanning centuries of wondering and decades of preparation, we finally saw it. The invisible made visible. The shadow cast by 4 million suns crushed into darkness. The heart of our galaxy revealed at last. We had weighed the monster. We had watched it bend time. We had traced the dances of stars caught in its grip. And now we had seen its silhouette, a perfect circle of absence, surrounded by light exactly where Einstein said it would be. Now we know it is there. We have seen its shadow. We have measured its pull. We have confirmed its existence beyond any doubt. But knowing something exists is not the same as understanding it. The questions have only begun. How big is this darkness really? What does it mean for a black hole to have size when it traps everything, even the light that would reveal its dimensions? And what is it doing to our galaxy? To answer, we must venture closer to the boundary that separates everything we know from everything we can never know. There exists a line in space around Sagittarius, a star beyond which nothing, not even light itself, can return. This boundary has a name, the event horizon. It is not a physical surface, not a wall you could touch, or a barrier you could see. It is something stranger, a threshold written into the geometry of space-time itself, a point where the rules of existence fundamentally change. The event horizon of Sagittarius, a star, measures 12 million miles across. To grasp this scale, imagine lining up 13 suns side by side, that distance stretching from one edge of our star to the other 13 times over equals the diameter of this invisible boundary. And yet compressed within this region sits the mass of 4 million suns, not scattered across that space, but concentrated into a single point at the center, pulling so hard that the boundary itself becomes inescapable. This is the essence of a black hole's strangeness. Its physical size, if such a concept even applies, is infinite. All its mass collapses to a point of zero volume, a singularity where density becomes meaningless. But the event horizon gives us something measurable, a circle drawn in space, marking the distance at which escape velocity equals the speed of light. Cross that line, and no force in the universe can bring you back. The horizon is not a thing. It is a condition, a place where space-time curves so sharply that all paths, even those taken by light, bend inexorably inward. You could fire a rocket engine at full thrust. You could move at nearly the speed of light, and still you would fall deeper into the abyss. Once inside, every direction points toward the center. Forward, backward, left, right, all roads lead to the singularity. What makes this boundary truly paradoxical is that it looks different depending on where you stand. Two observers watching the same event will see two completely different realities, and both will be correct. Imagine you are falling toward the event horizon. From your perspective, nothing unusual happens. As you approach, You do not feel a barrier. You do not see a warning sign. The stars around you begin to distort their light, bending into strange patterns as space-time warps. But you pass through the horizon smoothly, almost anticlimactically. To you, it is just another point in space. You continue falling, accelerating toward the center, your journey uninterrupted. But now, imagine someone far away, safely outside the black hole's grip, watching your descent through a powerful telescope. They see something entirely different. As you approach the horizon, you appear to slow down. Your movements become sluggish. Your signals take longer to reach them. The light from your spacecraft shifts redder and redder as time dilation takes hold. You drift closer to the boundary, and to the distant observer you slow even more. Minutes stretch into hours. Hours stretch into days. As you reach the very edge of the event horizon, you appear to freeze completely, hovering just above the boundary, your image growing dimmer and redder until it fades into invisibility. To them, you never quite cross. You remain suspended there, forever caught in a moment that never ends. Yet you crossed smoothly. No hesitation, no freezing. The paradox resolves only when you understand that time itself has fractured. Both experiences are real. Both are true. Time near the event horizon runs so differently from time far away that the two perspectives cannot be reconciled. They describe the same event from reference frames so distorted by gravity that they no longer share a common reality. Consider another thought experiment. You drop a clock through the event horizon. The clock itself feels nothing unusual. It continues ticking second by second, as it always has. Its gears turn, its hands move. Time flows normally for the clock. But you, watching from a safe distance, see the clock's ticks grow slower and slower. One tick per second becomes one tick per minute, then one per hour, then one per day. As the clock approaches the horizon, the intervals stretch toward infinity. The clock appears to stop frozen at the boundary, its final tick lasting forever. Yet the clock has not stopped. It crossed the horizon long ago and continues falling inward, ticking normally in its own frame of reference. You simply cannot see it anymore. The light carrying information about its continued existence cannot escape to reach you. The clock has passed beyond the veil into a region of space-time from which no information returns. This boundary reminds us of something profound. There are thresholds in existence that once crossed cannot be uncrossed. Choices that once made cannot be unmade. Moments that once passed cannot be revisited. The event horizon is the universe's most absolute expression of this truth. In life, we face our own horizons, doors we walk through, knowing we cannot return, words we speak that cannot be unspoken, decisions that alter the course of everything that follows. The universe places these boundaries not to trap us, but to remind us that time moves in one direction, that causality flows forward, that some transformations are permanent. The event horizon around Sagittarius, a star is 12 million miles wide, a sphere of inevitability surrounding the collapsed remnant of millions of suns. It is the ultimate one-way door, the final threshold, the boundary between the knowable universe and the unknowable void. Stand outside, and you remain part of everything, connected to the galaxy, to the flow of time, to the possibility of escape. Cross it, and you sever all connections. The universe you knew continues without you. Light, information, influence, none can follow where you have gone. This is the event horizon, Not a place, but a condition. Not a barrier, but a transformation. Not an ending, but a crossing into a realm where the rules we know no longer apply. And around the darkness at our galaxy's center, this boundary sits quietly marking the edge of forever waiting with the patience of space-time itself. But what creates this inescapable boundary? To understand, we must grasp gravity not as a force, but as a shape. Gravity is often described as a force, something that pulls objects toward each other. But Einstein taught us to see it differently. Gravity is not a pull, it is a shape, a curvature, a dimple in the fabric of space-time itself. And nowhere is this shape more extreme than around a black hole. Imagine space-time as a vast flat sheet stretched tight. Place a small marble on this sheet, something with the mass of Earth. The sheet sags slightly beneath it, creating a shallow depression. A nearby object might roll toward the marble, not because it is being pulled, but because it is following the slope of the curved sheet. This is Earth's gravitational well, gentle and forgiving. Now, place a bowling ball on the sheet, something with the mass of our sun. The depression deepens considerably. The slope steepens. Objects need more speed, more energy to climb out of this well. Earth orbits the sun, not because an invisible rope tethers it, but because it rolls endlessly around the slope of the sun's gravitational well, moving fast enough that it never falls in, but not fast enough to climb out. But now, imagine placing something incomprehensibly heavy on the sheet. 4 million bowling balls compressed into a point. The fabric does not merely sag, it plunges, it tears, it collapses into a funnel so steep, so deep, that the sheet itself disappears into a hole with no bottom. This is Sagittarius, a star's gravitational well. The well created by a black hole is not simply deep, it is infinite. No matter how far down you travel, there is always farther to fall. The slope steepens continuously as you approach the center, curving more and more sharply until space-time itself folds in on itself. At the event horizon, the slope becomes so steep that not even a light can climb back out. Beyond it, the well becomes something else entirely, a one-way path leading to the singularity at the center where all notions of distance and direction collapse. Yet this well's influence extends far beyond the event horizon. Gravity does not stop at any boundary. It reaches outward, weakening with distance, but never vanishing. From 26,000 light-years away, we feel the pull of Sagittarius, a star's gravitational well. Our sun, our solar system, every planet and moon and asteroid, all of us are rolling along the gentle, outer slopes of this cosmic funnel. We do not fall straight in because we are moving sideways fast enough that our trajectory curves around the well rather than into it. We complete one orbit every 240 million years, tracing a vast circle around the galactic center. But make no mistake, we are inside the well. We have always been inside it. We are passengers on a journey around an abyss we can never see. The well reveals itself in subtle ways. Light climbing out of it loses energy, stretching toward redder wavelengths. This is why we observe gravitational redshift in stars like S2 as they skim close to the black hole. The photons are not changing in any absolute sense. They are simply climbing a slope so steep that by the time they reach us, they have lost a measurable fraction of their energy. Stars orbiting near the edge of the well must move at extraordinary speeds to avoid falling in. S2 races at 17 million miles per hour, not because something is pushing it, but because at that distance from the black hole, moving any slower would mean spiraling inward. The star is perpetually falling, but falling sideways, fast enough that it misses the center, looping back out to climb the slope again. Other stars orbit closer still, their speeds even more extreme. These inner stars complete their circuits in just a few years, caught in the steepest regions of the well where space-time curves so sharply that even a slight loss of momentum would send them plummeting toward the event horizon. And at the bottom of this, well beneath the event horizon, lies something physics cannot fully describe: the singularity. This is not merely the deepest part of the well. It is where the well ceases to have meaning, a point where density becomes infinite, where space-time curvature becomes infinite, where the equations of general relativity break down and offer no answers. Some physicists imagine the singularity as a point of zero size, containing all the black hole's mass. Others suggest it might be a ring spinning with the black hole's rotation. Still others propose that quantum effects prevent true singularities from forming, replacing them with something else, a quantum core, perhaps unimaginably dense, but not infinite. But these are guesses. No observation can penetrate the event horizon to reveal the truth. The singularity remains hidden, forever sealed behind the boundary of no return. The Milky Way, then, is not a flat disk of stars. It is a funnel, a vast slope carved into space-time by the weight of the monster at its center. We live on the gentle outer rim of this funnel, where the curvature is barely noticeable, where gravity feels like the familiar pull of planets and stars. But deeper in the slope steepens. Closer still, it becomes precipitous, and at the very center, it becomes infinite, a throat so narrow and so deep that it swallows space-time itself. We drift along the surface of this funnel, held in place by our sideways motion, our orbit keeping us safely distant from the abyss. But the well is always there, extending upward to touch every corner of the galaxy. Everything within the Milky Way moves under its influence. Everything traces its path along slopes carved by 4 million suns collapsed to darkness. This is not a force pulling us. It is the shape of the universe we inhabit. We live inside a gravitational well, so vast it encompasses hundreds of billions of stars. And at the bottom, where the well has no end, sits the silent heart of our galaxy, a darkness so deep it bends, time traps light, and defines the destiny of everything within its reach. The well defines the shape of gravity. But when matter ventures too close, something violent awakens. Matter falling toward a black hole does not plunge straight in. It spirals, like water circling a drain, like leaves caught in a whirlpool. Anything drifting too close to Sagittarius, a star begins to rotate, pulled into an ever-tightening circle around the event horizon. This is not a gentle descent. It is a maelstrom of unimaginable violence, a cosmic storm raging in silence. The material forms what astronomers call an accretion disk, a vast ring of gas and dust spinning around the black hole. This disk is not static. It churns. It seethes. It glows with a heat so intense that temperatures reach millions of degrees. At these extremes, atoms themselves break apart. Electrons tear free from their nuclei. The disk becomes a plasma, a sea of charged particles spiraling inward at velocities approaching the speed of light. In other galaxies, Where black holes feed more aggressively, accretion disks shine with such brilliance that they outshine every star in their host galaxies combined. These are the quasars, cosmic lighthouses, visible across billions of light years, beacons powered by nothing more than matter falling into darkness. Their disks blaze continuously, consuming the equivalent of multiple suns every year, radiating more energy than entire galaxies. But Sagittarius A star is quieter. Our galaxy's center does not overflow with gas and dust the way more active galaxies do. The black hole feeds sparingly, catching only the occasional stray cloud or the outer layers of a star that wanders too close. Most of the time, the accretion disk glows faintly, its light dim and steady. From 26,000 light years away, it appears as little more than a faint smudge, barely distinguishable from the surrounding stars. Yet even in this relative calm, the physics at work is extreme. Within the accretion disk, friction dominates. As material spirals inward, it moves at different speeds depending on its distance from the black hole. Inner regions orbit faster than outer regions. This creates sheer a grinding motion where layers of plasma slide past each other at thousands of kilometers per second. The friction generated by this shear is staggering. Particles collide. Kinetic energy converts to heat. Temperatures soar into the millions of degrees. At such extremes, the disk radiates across the entire electromagnetic spectrum: radio waves, infrared, visible light, ultraviolet X-rays, even gamma rays. The hottest regions closest to the event horizon glow primarily in X-rays, their photons carrying energies thousands of times greater than visible light. But heat and friction are not the only forces at play. Magnetic fields thread through the accretion disk, twisted and amplified by the disk's rotation, into configurations that nature rarely achieves. These fields behave like invisible cables, looping and tangling as the plasma flows. Sometimes they snap, releasing energy in sudden bursts. Sometimes they reconnect, flinging particles outward at near light speed. These magnetic storms accelerate particles to relativistic velocities. Electrons and protons, caught in the grip of twisting field lines, spiral along magnetic pathways and rocket away from the disk at 99.9% the speed of light. In more active black holes, these particles form jets, narrow beams of matter and energy, shooting thousands of light years into space. Sagittarius A star does not currently produce such jets, but the magnetic infrastructure remains churning, quietly, occasionally, releasing bursts of energy that ripple across the galaxy. Every so often, the black hole awakens more dramatically. In 2019, astronomers monitoring Sagittarius A star in infrared light noticed something extraordinary. Over the course of a few hours, the black hole brightened by a factor of 75. It was as if the monster had suddenly opened its eyes, flaring with an intensity never before recorded. What caused this outburst remains uncertain. Perhaps a particularly dense clump of gas drifted into the accretion disk, compressing and heating as it spiraled inward until it ignited in a brilliant flash. Perhaps magnetic fields tangled into an unstable configuration and snapped, releasing stored energy all at once. Whatever the trigger, the flare served as a reminder that Sagittarius A star, though quiet compared to quasars, is far from dormant. Each time the black hole feeds, it leaves traces. X-rays pulse outward, detected by space telescopes orbiting Earth. Radio waves ripple through the galaxy, picked up by arrays of radio dishes scattered across continents. These signals carry information about the disk's structure, its temperature, its magnetic field strength. They are the echoes of matter's final moments before crossing the event horizon, the last messages sent from the edge of no return. In galaxies with more active black holes, these feeding frenzies never stop. Some supermassive black holes devour material continuously, their accretion disks blazing like cosmic furnaces. They consume stars' gas clouds, even other black holes that stray too close. Their light is so intense that it can sterilize entire regions of their host galaxies, preventing new stars from forming stripping atmospheres, from planets filling space with lethal radiation. Sagittarius, a star by contrast, eats intermittently. It waits. It bides its time. When a cloud of gas wanders near the black hole, captures it, feeding briefly before returning to its usual faint glow. This moderation is fortunate. If our galaxy's central black hole behaved like a quasar, the radiation pouring from the galactic core might make life far less likely throughout the Milky Way. Instead, the black hole's restraint allows the galaxy's spiral arms to remain calm, permits stars to form in peace, and gives planets like Earth the stability needed for life to emerge and evolve. Yet the potential for violence remains. Sagittarius, a star is not gentle because it lacks power. It is gentle because it lacks fuel. If a massive gas cloud were to fall into the galactic center, if a star were to be torn apart by tidal forces and scattered into the accretion disk, the black hole would flare to life. It would feast. And for a time, the heart of the Milky Way would blaze with the fury of a quasar, announcing the monster's presence across the cosmos. For now, though, the storm remains mostly silent. The accretion disk glows softly, radiating just enough to be detected by our instruments, but not enough to threaten or illuminate. Magnetic fields twist quietly. Plasma spirals inward at millions of degrees. Particles accelerate to near light speed and vanish across the event horizon. All of this happens in what appears, from our distant vantage, to be near total stillness. This is the paradox of the galactic center. It is one of the most violent regions in the universe, a place where matter is torn apart, where temperatures exceed the cores of the hottest stars, where magnetic fields reach strengths unimaginable anywhere on Earth. And yet, from 26,000 light years away, it looks like a candle flickering in the dark. Beautiful, serene, deceptive. The violence is real. The storm is real. The danger is absolute. But distance transforms terror into beauty. From here, the maelstrom becomes a glow. The chaos becomes stillness. And the most lethal environment we have ever discovered appears as nothing more than a faint point of light, barely visible among the countless stars. This is the silent storm at the heart of the Milky Way, a tempest of light and energy, of heat and magnetic fury, wrapped in an illusion of calm. It waits there, still glowing softly, ready to awaken whenever the universe delivers its next meal. The storm rages when fed, yet the black hole's true power lies not in violence, but in something stranger. How something so impossibly small can hold an entire galaxy in its grasp. If you could shrink the Milky Way down to the size of North America, Sagittarius, a star would be no larger than a single grain of sand. A speck, a dot, something you could hold between your thumb and forefinger so small it might slip through the cracks in the pavement. And yet this grain of sand controls everything from the Atlantic coast to the Pacific, from the frozen north to the southern deserts. Every mountain, every river, every city and forest moves under its influence. The disparity is almost absurd. The Milky Way stretches 100,000 light years from edge to edge. That is roughly 590 quintillion miles, a number so large it loses meaning. Within this vast expanse swirl 400 billion stars, each one a sun in its own right, many with their own families of planets, moons, asteroids, and comets. The scale is incomprehensible, the distances unimaginable. And at the center sits a black hole whose event horizon measures just 12 million miles across. To compare 12 million miles to 100,000 light years is to compare a pebble to a continent. The ratio is approximately 1 to 50 trillion. The black hole occupies an infinitesimally small fraction of the galaxy's volume. If you mapped the Milky Way and marked the black hole's position, even the finest pen would draw a dot larger than the black hole's true size. Yet without this tiny speck, the galaxy would not exist. Remove Sagittarius, a star, and the gravitational anchor holding the Milky Way together vanishes. The 400 billion stars, no longer bound by a central mass, would begin to drift apart. The spiral arms would unravel. The disk would disperse. Over billions of years, the galaxy would dissolve into a diffuse cloud of isolated stars, each one wandering alone through the void. The black hole functions like the axle of an immense wheel. The galaxy rotates around it, its stars tracing orbits that take hundreds of millions of years to complete. Our sun, along with its retinue of planets, circles the galactic center once every 240 million years. The last time we occupied this position in space, dinosaurs were just beginning to appear on Earth. The next time we return here, the continents will have shifted into unrecognizable configurations, and life, if it still exists, will have evolved into forms we cannot imagine. This anchoring effect is gravity's most fundamental property. Mass attracts mass. The more mass concentrated in one place, the stronger the pull. Sagittarius A star, despite its minuscule size relative to the galaxy, contains 4 million times the mass of our sun, more mass than all the stars within several light years of the galactic center combined. This concentration creates a gravitational well deep enough to influence the motion of stars tens of thousands of light years away. Yet even Sagittarius A star is modest compared to some black holes. In the galaxy Messier 87, a black hole weighing 6.5 billion solar masses 1,500 times heavier than ours sits at the center. Its event horizon spans a diameter larger than our entire solar system. If you placed it where the sun is, its edge would extend beyond the orbit of Neptune. This is the black hole whose image was captured first by the Event Horizon Telescope in 2019, 3 years before Sagittarius, a star's own portrait, was revealed. Compared to such titans, Sagittarius A star seems almost approachable. Its event horizon could fit comfortably inside the orbit of Mercury. Its influence, while vast, does not dominate the galaxy with the overwhelming force of its larger cousins. In some ways, this modesty makes it more remarkable. Here is a black hole, small enough, if small is the right word to study in detail, yet large enough to hold an entire galaxy in its grip. The comparison highlights something profound about the universe. Power does not always come from size. It comes from density, from concentration, from the degree to which mass is compressed into a small region of space. A star, the size of our sun, contains enormous mass, but spread across nearly 1,000,000 miles. A neutron star contains comparable mass compressed into a sphere just 10 miles wide, and a black hole takes this compression to its ultimate extreme. All the mass collapsed to a single point, creating a gravitational well that nothing, not even light, can escape. Our position within this gravitational landscape is fortuitous. At 26,000 light years from the galactic center, we orbit in what might be called the habitable zone of the Milky Way, not too close, not too far. Closer in the environment becomes hostile. Radiation from the accretion disk would sterilize planets. Tidal forces from the black hole's gravity would disrupt planetary systems. Stars crowd so densely that close encounters would destabilize orbits, flinging planets into interstellar space, or sending them plummeting toward the black hole. Farther out beyond the galaxy's visible edge, stars drift in lonely isolation, too distant to be firmly bound by the black hole's pull. These outer regions are darker, colder, more vulnerable to disturbances from neighboring galaxies. The spiral arms, where most star formation occurs, where planets are most likely to form and life most likely to emerge, exist in a middle zone, far enough from the center to be safe, close enough to be stable. Earth occupies this zone. We orbit a stable star in a quiet spiral arm, sheltered from the violence of the galactic core, anchored by the distant gravity of a black hole we have only recently learned to see. Our existence depends on this balance. Too close, and we would never have formed. Too far, and we might have been cast adrift, orphaned from the galactic family. In this sense, size truly is not everything. The smallest object in the galaxy, measured by volume, exerts the greatest influence. The grain of sand holds the continent. The speck controls the whole, not through force of presence, but through density of being, through the sheer concentration of mass into a region so small it borders on the incomprehensible. This is the paradox at the heart of black holes. They are points of near infinite density, masquerading as objects of finite size. Their event horizons give them boundaries we can measure and discuss, but their true nature, the singularity within, occupies zero volume. In a sense, they are everywhere and nowhere, infinitely small, yet cosmically powerful. Sometimes the smallest things hold the greatest power, not because they are large, but because of how they concentrate their essence. A heart, tiny compared to the body, pumps life through every vein. A seed smaller than a fingernail contains within it the blueprint for a towering tree. A single decision lasting only a moment can reshape an entire life. And at the center of the Milky Way, a grain of sand holds 400 billion stars in its invisible grasp. It does not need to be large. It does not need to dominate through presence. It simply needs to be dense enough, massive enough, concentrated enough that space-time itself bends in acknowledgement. We live in this galaxy because the grain of sand exists. We orbit within its gravitational well, have always orbited within it, and will continue to orbit for as long as the galaxy endures. The black hole is not optional. It is not decorative. It is foundational. Remove it, and the structure collapses. The Milky Way would cease to be a galaxy and become merely a dispersing cloud of stars scattering slowly into the void. But the grain remains, and around it, held in the embrace of its gravity, 400 billion stars, including ours, continue their ancient dance, small beyond measure, yet powerful beyond comprehension. This is Sagittarius A star. This is the heart of everything we know. The black hole holds the galaxy through gravity alone, but its influence goes deeper. It shapes the destiny of stars, feeds on the unwary, and occasionally devours them whole. Not all black holes are quiet. Across the universe, some blaze with such ferocity that they outshine entire galaxies. These are the quasars, the most luminous objects in existence, cosmic beacons visible across billions of light years. At their centers sit supermassive black holes, far more active than Sagittarius A star monsters that feed not sparingly, but voraciously consuming stars, gas clouds, and anything else that strays too close. A quasar's accretion disk does not glow faintly. It blazes. Matter spirals inward at such rates that the disk heats to temperatures exceeding billions of degrees. The light emitted is so intense that it can outshine all 400 billion stars of its host galaxy combined. From distant corners of the universe, astronomers see not the galaxy itself, but only the brilliant point at its center, the feeding black hole announcing its presence across cosmic distances. These active black holes devour material at staggering rates. Some consume the equivalent of multiple suns every year. A star wandering too close is not merely captured, it is torn apart by tidal forces stretched into ribbons of gas that spiral into the accretion disk and vanish within days. Gas clouds drifting near the galactic center are swallowed whole, compressed and heated until they shine with the luminosity of 1,000 supernovae. The radiation emitted by such feeding frenzies is not merely bright, it is lethal. X-rays and gamma rays pour from the accretion disk in torrents flooding the surrounding space with energy. This radiation can sterilize entire regions of a galaxy, preventing new stars from forming stripping atmospheres, from planets destroying the molecular clouds where life might one day emerge. In the most active galaxies, the central black hole becomes an engine of destruction, reshaping its environment through sheer radiant power. Some quasars produce jets, narrow beams of particles accelerated to near light speed by twisted magnetic fields. These jets shoot outward from the black hole's poles, stretching thousands or even millions of light years into space. When they strike nearby gas clouds, they create shock waves that ripple across the galaxy. The jets carry so much energy that they can heat intergalactic gas to millions of degrees visible in X-ray telescopes as vast glowing bubbles surrounding the host galaxy, Sagittarius. A star is nothing like this. Our galaxy's central black hole feeds sparingly, consuming material only when chance delivers it. Most of the time, the region around the event horizon remains dim and quiet, glowing just enough to be detected by sensitive instruments, but never approaching the brilliance of a quasar. It is as if the black hole, having once feasted, now rests in the shade, conserving its energy, waiting patiently for the next meal to arrive. This restraint is not by choice, it is by circumstance. The galactic center of the Milky Way simply does not contain enough material to sustain continuous feeding. Unlike more active galaxies, where dense clouds of gas constantly drift toward the center, our galaxy's core is relatively empty. The gas and dust that do exist are sparse, spread thin across vast distances. Only occasionally does a cloud wander close enough to be captured, and when it does, the feast is brief. Most of the time, Sagittarius A star glows faintly in radio waves and X-rays, radiating a mere fraction of the energy it could release if given more fuel. It is like a lion that has already eaten, lying in the grass, watching the world pass by with half-closed eyes. The potential for violence remains, but the hunger is satisfied. The predator sleeps. Yet the past tells a different story. Evidence suggests that Sagittarius A star was not always so quiet. Above and below the plane of the Milky Way, astronomers have detected two enormous structures called the Fermi bubbles, vast lobes of gamma-ray emission stretching tens of thousands of light-years into space. These bubbles are not new. They are ancient, the remnants of an event that occurred several million years ago. The most likely explanation is a burst of activity from Sagittarius A star itself. At some point in the relatively recent past, recent on cosmic timescales, the black hole consumed a massive amount of material all at once. Perhaps a giant gas cloud drifted into the galactic center. Perhaps a star wandered too close and was torn apart, its remains funneled into the accretion disk. Whatever the trigger, the result was a violent outburst. For a time, Sagittarius, a star blazed like a quasar. Energy poured from the accretion disk. Jets of particles shot outward from the black hole's poles, carving tunnels through the surrounding gas and inflating the bubbles we see today. The galactic center, normally dim and peaceful, flared to life with a brilliance visible across half the galaxy. And then, as quickly as it began, the outburst ended. The fuel ran out. The jets shut off. The black hole returned to its slumber. Today, the Fermi bubbles remain as scars glowing faintly in gamma rays, a reminder that the monster at our galaxy's heart is capable of far more than it currently displays. The bubbles span 50,000 light years, from top to bottom structures so vast that light takes 50 millennia to cross them. They are the echoes of a feast, the remnants of violence, on a scale almost impossible to comprehend. This restraint, this current quietness, is humanity's great fortune. If Sagittarius A star behaved like a quasar, the Milky Way would be a far more hostile environment. The radiation pouring from the galactic center would flood the spiral arms bathing planets in lethal X-rays and gamma rays. Star formation would be suppressed across vast regions. Planetary atmospheres would be stripped away. Life, if it could emerge at all, would face constant bombardment from high-energy particles. Earth would not exist as we know it. Our planet orbits in a calm region of the galaxy, far from the violence of the core, shielded by 26,000 light-years of distance. But if the black hole were continuously active, that distance might not be enough. The radiation would reach us faint but persistent, altering the conditions that allowed life to evolve over billions of years. We exist in part because the monster sleeps, but sleep is not permanent. The black hole remains capable of awakening at any time. If a massive gas cloud were to drift into the galactic center, a cloud with the mass of thousands or even millions of suns, Sagittarius A star would stir. The material would spiral into the accretion disk, heating and compressing until it ignited in a brilliant flare. For a time, the black hole would feed, as it once did, blazing with energy, announcing its presence across the galaxy. If a star wandered too close, pulled off course by gravitational interactions with its neighbors, tidal forces would tear it apart. The star's outer layers would be stripped away and funneled into the black hole, creating a sudden surge of material flowing into the accretion disk. Astronomers call these events tidal disruption events, and they are among the most spectacular phenomena in the universe. For months or even years, the dying star's remains would glow as they spiraled inward, creating a temporary flare visible across cosmic distances. Such events are rare, but not impossible. The galactic center is crowded with stars, and their orbits are constantly shifting, perturbed by gravitational interactions. Eventually, one will stray too close. When it does, the feast will begin. For now, though, the predator rests. Sagittarius, a star consumes only what chance delivers. A stray cloud here, a wisp of gas there. The accretion disk glows faintly. The magnetic fields twist quietly. The event horizon waits patient and inevitable for the next morsel to arrive. And the galaxy, sheltered by the black hole's restraint, continues its peaceful rotation, its stars forming and dying, its planets orbiting its life, evolving all under the shadow of a sleeping giant. This is the paradox of Sagittarius A star. It is the most powerful object in the galaxy, capable of reshaping the environment across tens of thousands of light years. It is a predator of unimaginable strength, able to devour stars and flood space with lethal radiation. And yet most of the time, it does nothing. It waits, it watches, it sleeps. We are here because of this sleep. Our existence depends on the black hole's moderation, on the fortunate circumstance that the galactic center lacks the fuel to sustain continuous activity. If we lived in a galaxy with a more active core, life might never have emerged. The conditions might be too harsh, the radiation too intense, the environment too unstable. But we are here, and the monster sleeps. It has slept for millions of years, stirring only occasionally, feeding briefly before returning to its quiet vigil. It will sleep for millions more, perhaps billions, until the next major event delivers enough material to awaken it fully. Yet we should never forget what it is. The black hole is not benign. It is not gentle by nature. It is dormant because circumstances allow it to be, not because it has lost its power. The potential for violence remains coiled and waiting, ready to unleash itself whenever the universe provides the opportunity. The monster sleeps, and fortunately, its slumber is the reason we exist. But never forget it is still a monster, and monsters, no matter how quiet, remain forever dangerous. Now we understand the monster. We have measured it, seen its shadow, learned how it operates. But one final question remains. What is our connection to it? We, the small beings on a pale blue planet, how does our fate intertwine with the fate of this darkness at the galaxy's heart? Right now, as you read these words, you might feel perfectly still. You are sitting, perhaps, or lying down, comfortable and motionless. The ground beneath you seems solid and unmoving. The air around you hangs calm. In this moment, you appear to be at rest, but you are not still. You have never been still. You will never be still. Beneath the illusion of stillness, you are moving at speeds that defy comprehension. The earth spins on its axis at 1,000 miles per hour. If you stand at the equator, you are rotating through space faster than the speed of sound, completing one full revolution every 24 hours. The ground beneath your feet is not a stationary platform, it is a spinning sphere hurtling through the void. And the Earth itself is not still. It orbits the Sun at 67,000 miles per hour, tracing a vast ellipse through space. Every second, you travel 18 miles along this orbital path. In the time it takes to read this sentence, you have moved hundreds of miles through the solar system, carried by a planet that never stops, never slows, never rests. But even this is not the full picture. The Sun does not sit motionless at the center of the solar system. It too is moving and carrying us with it. The Sun, along with all its planets, moons, asteroids, and comets, races through the galaxy at 515,000 miles per hour. That is more than 230 kilometers every single second. While you read this paragraph, you have traveled thousands of kilometers through space, pulled along by the Sun's journey around the galactic center. This motion is not random. It is an orbit. Just as Earth circles the Sun circles Sagittarius, a star. We are passengers on a cosmic voyage, tracing a vast loop around the black hole at the galaxy's heart. And this journey is almost incomprehensibly slow. One complete orbit, what astronomers call a galactic year, takes 240 million Earth years. The last time the Sun occupied this position in space, dinosaurs were just beginning to walk the Earth. Pangaea, the supercontinent, was breaking apart. The first mammals had not yet appeared. Forests of giant ferns covered the land, and the oceans teemed with creatures that no longer exist. Since then, entire epochs have risen and fallen. The dinosaurs dominated the planet for over 100 million years, then vanished in an instant of cosmic violence. Mammals evolved and diversified. Ice ages came and went. Continents drifted across the globe. Humans appeared built. Civilizations looked up at the stars and wondered. And through it all, the Sun continued its journey, carrying Earth and everything on it around the hidden monster at the galaxy's center. We have not yet completed a full orbit since the dinosaurs emerged. We are still making the same loop, still traveling the same path, passengers on a voyage that began long before life ever wondered about its origins. What will Earth be like when we return to this position again? 240 million years from now, the continents will have shifted into unrecognizable shapes. The climate will have changed in ways we cannot predict. The species alive today, humans included, will likely be long extinct, replaced by descendants we cannot imagine. The stars in the night sky will have rearranged themselves into new patterns, familiar constellations, dissolved ancient myths forgotten. But the journey will continue. The Sun will keep orbiting Sagittarius. A star will keep pulling, and the galaxy will keep turning indifferent to the fleeting lives that unfold on one small planet in one quiet arm. As the Sun carries us around the galaxy, we pass through different regions of space. Sometimes we drift through the dense, spiral arms where stars crowd close together and new suns are born in glowing clouds of gas. The night sky during these passages would be spectacular if anyone were around to witness it, filled with brilliant young stars and luminous nebulae. At other times, we travel through quieter regions between the arms where Stars are sparse, and the darkness runs deeper. The sky dims, the constellations shift. Over millions of years, the familiar patterns we have known throughout human history dissolve and reform into shapes our ancestors would not recognize. The sky, then, is not eternal. The stars we see are not fixed. They drift slowly, but inexorably, their positions changing as the galaxy rotates. The Big Dipper, Orion, the Southern Cross, all of these will eventually fade and scatter as the stars that form them move along their own orbits, each following its own path around the galactic center. In 1,000,000 years, the night sky will look subtly different. In 10 million years, it will be unrecognizable. The constellations that guided ancient sailors and inspired timeless myths will be gone, replaced by new patterns that future beings, if any exist, will name according to their own stories. And yet throughout this cosmic journey, we feel nothing. No wind of motion, no sensation of speed, no hint that we are hurtling through space at 500,000 miles per hour. Why? Because everything around us moves at the same velocity. The air, the ground, the oceans, the clouds, all of it travels together, bound to Earth, which is bound to the sun, which is bound to the galaxy. We move as one system, and within that system, motion becomes invisible. It is like sitting in an airplane cruising smoothly at altitude. Inside the cabin, you can walk, drink a cup of coffee, read a book, all without feeling the 600 miles per hour at which the plane travels. The motion is there, constant and real. But because everything in your immediate environment shares that motion, it becomes undetectable. The same principle applies on a cosmic scale. We do not feel the Earth's rotation because the atmosphere rotates with us. We do not feel the Earth's orbit because the entire planet shares that velocity. And we do not feel the sun's journey around the galaxy because the solar system moves as a unified whole. But the motion is real. Every moment you have ever experienced, every breath, every heartbeat, every thought has occurred aboard a cosmic vessel racing through space. Your first cry as a newborn, your first steps, your first kiss the moment you fell in love, the times you felt grief or joy or wonder, all of it happened while you were traveling at 515,000 miles per hour around a supermassive black hole. You are not a stationary observer watching the universe unfold. You are a traveler. You have always been a traveler. From the moment you were born until the moment you die, you will never stop moving through space. The Earth carries you. The Sun carries Earth. And Sagittarius, a star, pulls the Sun forward on an orbit so vast that civilizations rise and fall in the time it takes to complete a single loop. This is the truth of existence. We are cosmic voyagers, whether we know it or not. Passengers on a planet orbiting a star circling a black hole. All of it bound together by gravity into a system so vast and so intricate that the human mind struggles to comprehend its scale. Every ancient philosopher who wondered about the nature of motion, every scientist who measured the speed of light, every child who looked up at the stars and asked where we are going, all of them were standing on a platform that was never still. All of them were moving through the galaxy, just as we are now, just as every generation, before and after, will continue to move for as long as the sun endures. The journey has no destination. There is no endpoint, no final stop. The orbit simply continues, endlessly circling the darkness at the galaxy's heart. We are not going anywhere in particular. We are simply moving through space and time, tracing a path that has been carved into the structure of the galaxy itself. And so, the next time you feel, still remember this, you are flying. You have always been flying, and you will never stop. We are travelers on an endless journey, but we do not travel alone. Every star in the sky shares this voyage, bound by the same invisible force that holds the galaxy together. 400 billion stars orbit Sagittarius A star. Not a few million, not even a few billion. 400 billion, each one a sun in its own right, many larger and brighter than ours, many older, many younger, and all of them, every single one, bound to the same invisible anchor at the galactic center. It is as if the Milky Way were a vast harbor, and every star a ship tethered to a single mooring point. The chains are invisible, made not of metal, but of space-time itself, curved and shaped by the black hole's immense gravity. Yet they are no less real. Every star feels the pull. Every orbit is dictated by it. There are no exceptions. The nearest stars to the galactic center orbit just a few light years away, racing around the black hole in paths measured in decades rather than millions of years. These inner stars move so fast that astronomers can watch their positions change over a human lifetime, tracking their ellipses as they whip past the event horizon and swing back out into the relative safety of the surrounding space. Farther out, stars take longer to complete their orbits. In the spiral arms where our sun resides, the journey takes hundreds of millions of years. At the galaxy's outer edges, where starlight fades and darkness deepens, the orbits stretch to nearly 1 billion years. Yet even there, 26,000 light years from the center, 50,000 light years, even 70,000 light years away, stars still feel the pull of Sagittarius, a star, faint but unmistakable, distant but inescapable. This is the black hole's true reach, not the 12 million miles of its event horizon, but the 100,000 light years across which its gravity extends. It does not need to touch a star to control it. It does not need to be visible to command its motion. Gravity requires no medium, no contact, no line of sight. It simply is reaching across empty space to bind every star in the galaxy into a single unified system. Without this anchor, the Milky Way would not exist. The stars would drift apart, their motions no longer synchronized, their paths no longer held in common orbit. Over time, the spiral arms would dissolve. The galactic disk would thin and scatter. 400 billion stars, once bound into a majestic structure, would become orphans, wandering alone through the void with no home to return to. The black hole, then, is not merely located at the galaxy's center. It is the reason the galaxy has a center at all. It is the foundation upon which everything else rests. Remove it, and the structure collapses. The Milky Way would cease to be a galaxy and become merely a dispersing cloud of isolated stars. But the black hole is not the only force at work. Beyond the visible stars, beyond the gas and dust, beyond everything we can see with telescopes, lies another presence, dark matter, a substance that does not emit light, does not absorb light, does not interact with ordinary matter, except through gravity. and yet it is everywhere, forming a vast halo around the galaxy, contributing far more mass than all the stars combined. If Sagittarius A star is the anchor at the center, dark matter is the scaffolding that holds the outer regions in place. Together, they create a gravitational landscape that keeps the galaxy stable. The black hole pulls the inner stars into tight, fast orbits. Dark matter spread across a much larger volume provides the mass needed to bind the outer stars, preventing them from flying off into intergalactic space. This partnership is essential. Neither could maintain the galaxy alone. The black hole, for all its power, contains only 4 million solar masses, a tiny fraction of the galaxy's total. Dark matter, though far more abundant, is diffuse, spread too thin to create the concentrated pull needed at the center. But together, they shape the gravitational well that defines the Milky Way structure. Every star orbits within this well. Every planet, every moon, every asteroid, every grain of dust, all of it bound by invisible forces, moving in patterns dictated by mass we can measure, but often cannot see. The chains are real, and they hold everything together. If the black hole were to vanish, an impossibility, but imagine it, the consequences would unfold over millions of years. At first, nothing would seem to change. The stars nearest the galactic center would continue their orbits, carried forward by momentum. But gradually, their paths would drift. Without the central mass to anchor them, their velocities would carry them outward away from the core. The spiral arms would lose their coherence. Stars would scatter, some moving faster, some slower, no longer synchronized. The beautiful structure we see in images of the Milky Way, the graceful curves, the luminous arms, the glowing core would dissolve into formless chaos. Our sun would drift as well. The solar system, no longer bound to a galactic orbit, would wander through space with no destination. We would become nomads, isolated from the galactic community, drifting through the dark with no home to return to. The night sky would slowly empty as other stars also set adrift, moved in different directions, their light fading with distance until we were alone in the void. But the black hole does not vanish. It remains patient and inevitable, anchoring the galaxy with the pure force of its gravity. And because it remains, we remain. The solar system stays bound to its orbit. The galaxy holds its shape. The stars continue their ancient dance. Every breath you take happens on a planet held in place by this invisible chain. Every heartbeat, every thought, every moment of joy or sorrow occurs within a system bound to Sagittarius A star. You may never see the black hole. You may never feel its pull, but it is there, always exerting its influence across 26,000 light years of space. This is the deeper truth of existence. Nothing is independent. Nothing stands alone. Every atom in your body was forged in the core of a star, scattered into space by a supernova, gathered into clouds of gas and dust, collapsed under gravity into a new solar system. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of it came from stars that once orbited the same black hole we orbit now. You are made of the galaxy, and the galaxy is held together by darkness. From the smallest particle to the largest structure, everything is connected. Atoms bond into molecules. Molecules form cells. Cells build bodies. Bodies live on planets. Planets orbit stars. Stars orbit black holes. and black holes anchor galaxies. It is a hierarchy of connection, each level bound to the next by forces that may be invisible but are never absent. Gravity is the weakest of these forces. An ordinary magnet can overcome Earth's entire gravitational pull, lifting a paperclip off a table. Yet, gravity is also the most far-reaching. It never turns off. It never fades completely. It simply weakens with distance, spreading outward, infinitely touching everything, binding everything, connecting everything. And at the center of our galaxy, concentrated into a region 12 million miles wide, sits a mass so great that its gravity reaches across the entire Milky Way, 400 billion stars held in orbit by a single invisible anchor, 400 billion chains, all leading back to the same point of darkness. We think of ourselves as independent. We imagine that our lives are separate from the cosmos, that what happens in distant space has no bearing on us here. But this is an illusion. We are part of the system. We have always been part of it, and we will remain part of it for as long as the galaxy endures. Every star in the sky is your distant companion on this journey. Every photon of starlight that reaches your eyes has traveled for years or centuries, carrying a message from another part of the galaxy. And all of it, the stars, the light, the planets, the space between, is held together by the same force that keeps you grounded to Earth. Nothing is independent. Everything is connected, and at the center of it, all silent and unseen, Sagittarius. A star holds the invisible chains that bind the galaxy into one. We orbit the black hole. We always have. But what would it be like to live closer to the darkness? What if we traded our safe distance for proximity to the heart of everything? Imagine for a moment that Earth did not orbit the sun in the quiet safety of a spiral arm. Imagine instead that our planet occupied the orbit of S2, that racing star we watched earlier, the one that screams past the galactic center every 16 years at 17 million miles per hour. What would life be like in such a place? What would the sky look like? And could life exist at all? The first thing you would notice is the sky itself. Look up, and Sagittarius. A star would dominate half the heavens, not as a point of light, but as an absence, a perfect circle of absolute blackness stretching from horizon to zenith. The event horizon, 12 million miles wide, would loom so large that it would feel less like an object in the distance and more like a hole torn through reality itself. Around this darkness, light would behave in ways that seem impossible. Starlight from behind the black hole would bend around its edges, creating luminous arcs and rings that shimmer and distort. Some stars would appear in multiple places. At once, their images duplicated by gravitational lensing. A star directly behind the black hole might appear in front of it, its light curved so sharply by gravity that it wraps entirely around the event horizon before reaching your eyes. The view would be beautiful in a deeply unsettling way, geometric, alien, a reminder that the rules of light and space are not what they seem. The black hole would not merely block your view, it would warp it, bending and twisting the cosmos into shapes nature never intended. But the darkness would not be the only feature of the sky. Around you, thousands of stars would crowd together, packed so densely that true night would never fall. At the galactic center, stars are separated not by light years, but by mere light weeks, sometimes light days. The sky would blaze continuously, a perpetual twilight filled with the glow of countless suns. Yet this brilliance would bring no warmth, no comfort. The light would be accompanied by something far more sinister: radiation. X-rays and gamma rays pour constantly from the accretion disk around Sagittarius A star, invisible to the eye, but lethal to life. This radiation would bombard any planet in the vicinity, stripping away its atmosphere within days, perhaps hours. Earth's protective magnetic field and ozone layer, which shield us from the sun's relatively gentle radiation, would be utterly inadequate here. The high-energy photons streaming from the black hole's surroundings would penetrate deep into the atmosphere, ionizing molecules, breaking apart chemical bonds, destroying the delicate balance that makes life possible. Within days, the atmosphere would begin to evaporate. Oxygen and nitrogen, no longer held in place by a stable climate, would be stripped away by the relentless onslaught of radiation. The oceans exposed to the harsh glare of X-rays, and the heat of the accretion disk would boil. Water vapor would rise into the thinning atmosphere and be torn apart by ultraviolet light, its hydrogen escaping into space, its oxygen consumed by chemical reactions with the scorched surface. Within weeks, Earth would be a barren rock. No air, no water, no life. Just a dead world, slowly spiraling closer to the event horizon. But atmospheric loss would not be the only danger. Tidal forces near the black hole would tear the planet apart. Gravity does not pull uniformly. The side of Earth closer to Sagittarius, a star would feel a stronger pull than the side farther away. This difference, called a tidal force, is the same effect that causes ocean tides on Earth due to the moon's gravity. But near a black hole, the effect is extreme. The planet would be stretched along the axis, pointing toward the black hole, and compressed along the perpendicular axis. Earth would deform, buckling and cracking under the strain. The surface would heave. Mountains would crumble. Oceans, if any remained, would slosh violently from one hemisphere to the other. Earthquakes of unimaginable magnitude would shake the planet continuously. Eventually, the tidal forces would exceed the structural strength of rock itself. Earth would fracture. Pieces would break away, pulled toward the black hole by gravity stronger than the planet's own cohesion. The fragments would spiral inward, joining the accretion disk, glowing briefly before crossing the event horizon and vanishing forever. This is the fate of anything that ventures too close. Not just planets, but moons, asteroids, even stars. Tidal forces do not discriminate. They simply tear apart whatever cannot resist their pull. And there is another danger still. Near the galactic center, stars are packed so closely that their orbits occasionally intersect. Close encounters between stars are rare in the outer galaxy. Our sun, for instance, will likely never come close to another star in its entire lifetime. But near the core, where stars crowd together, such encounters happen regularly. When two stars pass close to each other, their gravitational fields interact. Planets orbiting one star can be pulled toward the other. Some are captured, becoming part of a new system. Others are flung outward, ejected into interstellar space, with enough velocity to escape the galaxy entirely. These rogue planets wander forever through the void, orphaned and alone, never again to feel the warmth of a sun. Even if a planet survived the tidal forces, even if it somehow retained its atmosphere. Against the radiation, the chaotic gravitational environment near the galactic center would make stable, long-lived planetary systems almost impossible. Orbits would shift, climates would destabilize. Life, if it somehow emerged, would face conditions changing too rapidly for evolution to keep pace. This is why we are fortunate. Our position 26,000 light-years from the galactic center places us in what might be called the galactic habitable zone, not too close to the core, where radiation and tidal forces dominate, not too far out where stars drift in isolation, vulnerable to disturbances from passing galaxies or dark matter fluctuations. We occupy the middle ground close enough to remain bound to the galaxy's structure, far enough to avoid its most violent regions. From here, Sagittarius A star is invisible to the naked eye, hidden behind dust and distance. Its radiation is diluted across 26,000 light-years, arriving faint and harmless. Its tidal forces are imperceptible. We orbit in peace, sheltered by the vastness of space from the dangers that lurk at the galaxy's heart. Sometimes, happiness is not found in proximity to the things we admire. It is found in appreciating them from a safe distance. We do not need to stand at the center to be part of something larger. We do not need to touch the black hole to be shaped by it. Our lives unfold here, in this quiet corner of the galaxy, and that is enough. The black hole holds us in its gravitational embrace, but it does not threaten us. It anchors the galaxy without consuming it. It shapes our orbit without dictating our fate, and from this distance, we can marvel at its power, study its mysteries, and understand its role in the cosmos, all while remaining safely beyond its reach. We are not at the center, but we are exactly where we need to be, and in a universe filled with danger, chaos, and incomprehensible forces that is a kind of grace. We are safe now, in this moment, in this place. But the universe does not remain still. The future holds changes we can predict and others we cannot. What lies ahead for the galaxy and for us? For now, our orbit is stable. The solar system traces its path around Sagittarius, a star without disturbance, completing one circuit every 240 million years. The black hole, for all its power, does not threaten to swallow us. Barring some catastrophic and unlikely event, Earth will continue orbiting the Sun, and the Sun will continue orbiting the galactic center for billions of years to come. But the universe does not stand still, and in the deep future, the Milky Way itself will change in ways both predictable and profound. 4 billion years from now, something extraordinary will happen. The Andromeda Galaxy, our nearest large neighbor, will collide with the Milky Way. This is not speculation, it is certainty. Andromeda is already moving toward us at 250,000 miles per hour. The gap between our galaxies shrinks by millions of miles every day, and one day it will close entirely. When people hear the word collision, they imagine violence, explosions, impacts, destruction. But galactic collisions are not like car crashes. They are slow, graceful, almost ghostly. Galaxies are not solid objects. They are mostly empty space, dotted with stars separated by unimaginable distances. When two galaxies merge, their stars do not crash into each other. They pass by millions of miles apart, their orbits disturbed, but their structures intact. What collides is not the stars, but the gravitational fields. As the Milky Way and Andromeda interpenetrate, Their combined gravity reshapes both galaxies. The spiral arms dissolve. The orderly rotation breaks down. Stars are flung into new orbits, some sent careening toward the merged core, others ejected into intergalactic space. The process will take hundreds of millions of years. From Earth, if Earth still exists, the night sky will transform slowly but dramatically. The Andromeda Galaxy, currently a faint smudge, visible only through binoculars, will grow larger and brighter over the millennia. Eventually, it will fill half the sky, a vast spiral looming overhead, its light illuminating the night like a second Milky Way. As the merger progresses, new stars will form. The collision compresses gas clouds, triggering bursts of star formation across both galaxies. For a time, the combined system will blaze with the light of billions of newborn suns. Then, as the gas is consumed, star formation will slow, and the merged galaxy will settle into a new configuration, no longer a spiral, but an elliptical galaxy, a glowing sphere of stars with no distinct arms or structure. And at the center of this new galaxy, two supermassive black holes will dance. Sagittarius, a star weighing 4 million solar masses, will encounter Andromeda's central black hole, which weighs roughly 100 million solar masses. At first, they will orbit each other at a distance, tracing wide ellipses through the chaotic core of the merging galaxy. But over time, friction with surrounding gas and gravitational interactions with passing stars will drain energy from their orbit. The black holes will spiral closer. Their orbital period will shrink from millions of years to thousands, then to mere decades. As they approach each other, they will begin emitting gravitational waves, ripples in space-time itself, carrying energy away from the system. These waves, predicted by Einstein and first detected in 2015, will grow stronger as the black holes draw near. Finally, after millions of years of spiraling inward, the two black holes will merge. In the final moments before collision, they will orbit each other hundreds of times per second, spinning faster than the human mind can comprehend. And then in an instant, they will collide. Space-time itself will shudder. The merged black hole will ring like a bell, sending gravitational waves rippling across the universe. The result will be a single, supermassive black hole weighing roughly 104 million solar masses, larger than either parent, more powerful, a new anchor for the new galaxy. What will happen to the solar system during all of this? The answer is uncertain. Our sun, along with its planets, might be flung into a higher orbit farther from the galactic center. It might drift into a lower orbit closer to the core. It might even be ejected, entirely cast out into intergalactic space to wander alone between galaxies. But the most likely outcome is survival. The solar system is small, and space is vast. The odds of a direct encounter with another star, even during a galactic merger, are extraordinarily low. More likely, we will simply be jostled. Our orbit shifted, our trajectory altered, but our structure intact. The sun will keep shining. The planets will keep orbiting. And life, if any, still exists on Earth 4 billion years from now, will witness the most spectacular cosmic event in the history of the galaxy. But the story does not end there. Even after the merger, even after the galaxies settled into their new configuration, time continues its march. And in the deep future, measured in trillions of years, the galaxy will face its final transformation. Stars do not shine forever. They burn through their fuel, fusing hydrogen into helium-helium, into carbon-carbon, into heavier elements, until they can no longer sustain fusion. Small stars, like our sun, will swell into red giants, then collapse into white dwarfs, dense cooling embers that fade slowly over billions of years. Larger stars will explode as supernovae, scattering their matter into space and leaving behind neutron stars or black holes. Over trillions of years, star formation will cease. The gas clouds that give birth to new stars will be consumed, and no new generations will replace the old. One by one, the stars will go out. The galaxy will grow darker, colder, quieter. The remaining stars will continue orbiting the central black hole, but their paths will gradually destabilize. Gravitational interactions between stars will occasionally fling some into higher orbits, while others sink closer to the core. Over unimaginable stretches of time, some stars will gain enough energy to escape the galaxy, entirely ejected into the void. Others will spiral inward, eventually crossing the event horizon and vanishing into the black hole. Slowly, inexorably, the black hole will grow. It will consume stars, gas planets, even other black holes. It will become the last remaining object in the galaxy, a lone survivor in an ocean of darkness. But even black holes do not last forever. In 1974, Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation is incredibly faint, far too weak to measure with current technology. But over timescales that dwarf the current age of the universe, it will cause black holes to evaporate. The process is slow. A black hole, the mass of Sagittarius A star, would take 10 to the power of 100 years to evaporate completely, a number so large it is almost meaningless. The universe itself is only 14 billion years old. But given enough time, even the largest black holes will fade, releasing their energy back into the cosmos as a faint hiss of particles and radiation. And then, at the end of everything, the black hole will vanish. The last anchor of the galaxy will dissolve, and space, once filled with stars and light and motion, will return to darkness and silence. This is the ultimate fate of all things. Nothing lasts forever. Not stars, not galaxies, not even black holes. The universe does not stand still. It changes constantly and inevitably driven by processes too slow for us to witness, but too powerful to resist. Yet here, in this moment, the galaxy endures. Stars shine, planets orbit, life persists. The black hole at the center holds everything together, and the future, though uncertain, is still unwritten in a universe where forever does not exist, where everything eventually fades. The fact that we are here, now that we can look up at the stars, that we can wonder about black holes, that we can trace the long arc of cosmic history, is itself extraordinary. The galaxy will change. The black hole will change. Even the universe will end. But right now, in this fleeting moment, we are here. And that is a kind of miracle. We have journeyed far from the discovery of an invisible monster to the distant future, when even darkness fades. But what does it all mean? What have we learned about this black hole? And what does it tell us about ourselves? We began with a mystery, a patch of darkness at the center of our galaxy, hidden behind curtains of dust, invisible to telescopes, silent to the human eye. For centuries, humanity looked toward the galactic core and saw nothing. No light, no answers, only questions whispered across 26,000 light years of space. But questions, when pursued with patience and care, lead to understanding. And so, step by step, we peeled away the veil. Radio telescopes listened where optical telescopes could not see. Infrared instruments pierced the dust. Mathematics revealed what eyes could not perceive. And slowly the invisible became known. What we found was extraordinary. Not a cluster of stars, not a cloud of gas, but a supermassive black hole weighing 4 million times the mass of our Sun, compressed into a region just 12 million miles across. A singularity wrapped in an event horizon, a point of infinite density surrounded by a boundary from which nothing, not even light, can return. Sagittarius A star. The name is simple, almost mundane, but the object it describes defies every intuition we carry about how the universe should work. It bends space, it warps time, it traps light itself, and it holds an entire galaxy, 400 billion stars, in its gravitational grip. When measured against the scale of the Milky Way, Sagittarius, a star is unimaginably small. If the galaxy were the size of North America, the black hole would be a single grain of sand. Yet this grain of sand controls everything from coast to coast. Without it, the galaxy would not exist. The spiral arms would unravel. The stars would drift apart. The structure we call home would dissolve into formless chaos. This is the first lesson the black hole teaches us. Size is not power. Concentration is power. A star the size of our Sun contains enormous mass, but spread across nearly 1 million miles. A neutron star contains comparable mass, compressed into a sphere just 10 miles wide. And a black hole takes this compression to its ultimate extreme, infinite density in zero volume, creating a gravitational pull so strong that space-time itself collapses around it. In life, we often mistake visibility for importance, loudness for influence, size for strength. But the most powerful forces are often the quietest. Gravity, the weakest of the fundamental forces, is also the most far-reaching binding galaxies across the universe. Love, invisible and unmeasurable shapes, lives more profoundly than any material possession. Ideas weightless and intangible have moved civilizations and rewritten history. The black hole reminds us that what matters is not how much space something occupies, but how deeply it influences what surrounds it. The second lesson concerns time. We grow up believing time is universal, that seconds tick at the same rate everywhere, that clocks measure an absolute and unchanging progression. But this is an illusion, born of our limited experience. Time is not a river flowing uniformly across the cosmos. It is woven into the fabric of space-time itself, and wherever mass warps space, it warps time as well. Near Sagittarius, a star time slows. Clocks tick more sluggishly. Light stretches and reddens as it climbs out of the gravitational well. A star skimming close to the event horizon experiences seconds, while the distant universe ages by minutes, hours, years. At the boundary itself, time appears to stop entirely. For outside observers, though, for anything crossing the horizon, time continues normally. This bending of time is not theoretical. It is real, measurable, confirmed. We observe it in the gravitational redshift of starlight. We account for it in GPS satellites. We test it every time we send a spacecraft into orbit. Time is relative, shaped by gravity, different for every observer depending on where they stand in the universe's gravitational landscape. And if time itself can bend, can stretch, can slow what else that seems absolute might be negotiable, what other certainties might dissolve when examined closely enough? The black hole teaches us humility before the strangeness of reality. The third lesson is about light. For most of human history, light represented the fastest, most absolute phenomenon we knew. Nothing could outrun it. Nothing could stop it. Light was the ultimate constant, the one thing that did not change. But at the edge of a black hole, even light fails. Photons streaming away from the event horizon are pulled back, their paths bent into inward spiraling curves until they vanish across the boundary. The fastest thing in the universe becomes trapped helpless against the pull of gravity. This is a profound realization. If light itself can be captured, if even the swiftest thing we know cannot escape, then escape velocity becomes meaningless near a black hole. There is no speed fast enough, no force strong enough, no technology advanced enough to break free once the horizon is crossed. The black hole represents an absolute limit, a boundary where the rules we rely on cease to apply. Yet light does more than fail near the black hole it reveals. The photograph captured by the Event Horizon Telescope shows not the black hole itself, but its shadow outlined by the glow of light bent and magnified around it. In this sense, light becomes the tool by which we see darkness. The absence is defined by what surrounds it. We know the invisible by observing what happens to the visible. The fourth lesson is about space. We imagine space as a stage on which events unfold, an empty backdrop against which matter moves. But space is not passive. It is dynamic, flexible, responsive to the presence of mass. Near a supermassive black hole, space curves so sharply that straight lines become circles, and all paths lead inward. This curvature is not metaphorical. It is literal. Space itself bends, and objects moving through that space follow the curves. Stars orbit Sagittarius. A star not because an invisible force pulls them, but because space-time itself is shaped like a funnel, and they are rolling along its slopes. Gravity is geometry. Mass tells space how to curve, and space tells matter how to move. Understanding this changes everything. The universe is not a collection of objects floating in emptiness. It is a woven fabric, a tapestry of space-time that flexes and warps wherever mass exists. We do not live on a stage. We live within the stage itself, part of a structure that responds to our presence, even as it shapes our motion. The fifth and deepest lesson is about connection. Nothing in the universe is truly independent. Every atom, every particle, every star is bound to every other through forces that may be invisible but are never absent. Gravity connects the smallest pebble to the largest galaxy. Light carries information across billions of light years, linking distant corners of the cosmos. Time flows differently in different places, but it flows for everyone, connecting all moments into a single unfolding story. We are part of this web. The atoms in our bodies were forged in the cores of stars that exploded billions of years ago. The oxygen we breathe, the carbon in our cells, the iron in our blood, all of it cycled through stellar furnaces, scattered into space, gathered into new clouds, and eventually incorporated into the planet we call home. We are made of stars, literally, not poetically, but factually, and those stars orbit Sagittarius, a star as do we. Every breath we take, every heartbeat, every thought occurs within a system, bound to the black hole. at the galaxy's center. We may never see it, we may never feel its pull directly, but we are connected to it through the invisible chains of gravity that hold the Milky Way together. This connection extends beyond physics. It touches something deeper, a realization that we are not separate from the cosmos, but part of it. We are not observers standing outside the universe looking in. We are participants woven into the same fabric that contains stars, galaxies, and black holes. Our existence is not incidental. It is a natural expression of the universe becoming aware of itself. When we look at Sagittarius A star, we are matter that has arranged itself in such a way that it can study other matter. We are the universe examining its own structure, asking questions about its own nature, marveling at its own complexity. This is extraordinary. In all the vastness of space, in all the billions of galaxies the universe has produced, beings capable of wonder, creatures small enough to fit on a single planet, yet capable of measuring objects millions of times more massive, minds limited to a few decades of life, yet able to comprehend timescales spanning billions of years. We are small. There is no denying that. Earth is a pale blue dot orbiting an average star in the outer regions of an ordinary galaxy. The entire history of humanity, every empire, every war, every discovery, every work of art has unfolded on a speck of rock so small that it would be invisible from the galactic center. But we are also extraordinary. We have built instruments that can see across the universe. We have developed mathematics that can describe the bending of space-time. We have taken a photograph of a black hole's shadow, capturing the outline of something that, by definition, cannot emit light. We have measured the unmeasurable seen, the invisible, understood the incomprehensible. This is not arrogance. It is a recognition of what consciousness can achieve. Against all odds in a universe governed by entropy and decay, complexity has emerged. Life has arisen. Minds have developed. And those minds have turned their attention outward, asking the oldest and deepest questions. Where are we? What are we? Why does anything exist at all? Sagittarius. A star does not answer these questions, but it helps us frame them. It shows us our place in the cosmos, not at the center, but not insignificant either. We orbit within a galaxy held together by darkness, but we do so with eyes open, with minds curious, with hearts that wonder. Sometimes the things that hold us together are the things we cannot see. In the galaxy, it is gravity, an invisible force, reaching across empty space to bind the stars into structure. In life, it is love, trust, hope, intangible forces that shape our choices and define our relationships. We cannot photograph love. We cannot weigh trust. We cannot measure hope in units. But we know they exist because we see their effects. The black hole is the same. We cannot see Sagittarius A star directly. We cannot touch it or visit it or fully comprehend what lies beyond its event horizon. But we know it is there because of what it does, because of the stars that dance around it, because of the light that bends near it, because of the galaxy it holds together. And in this, there is a kind of comfort. We live in a universe where the most important things are often invisible, where power comes not from size, but from depth, where connection exists even when we cannot see the threads, where meaning emerges not from being at the center, but from being part of something larger than ourselves. We do not need to stand at the galactic core to matter. We do not need to touch the black hole to be shaped by it. Our lives unfold here in this quiet corner of the Milky Way, and that is enough. We are connected to the black hole, to the galaxy, to the universe itself, not by proximity, but by the simple fact that we exist within the same fabric of space-time. Every moment you've lived has occurred aboard a planet orbiting a star, orbiting a black hole. Your first breath, your first word, every time you have felt joy, grief, wonder, or love. All of it happened while flying through space at 500,000 miles per hour, bound by invisible forces to a darkness you cannot see. You are a cosmic traveler. You always have been, and you are part of something vast, ancient, and beautiful, a galaxy held together by gravity, lit by stars, and made meaningful by the presence of beings who can look up and ask why. Tonight, as you drift toward rest, let this thought settle gently. Somewhere in the silence of space, 26,000 light years away, a black hole sits at the heart of everything. It does not shine. It does not call out. It simply is patient, inevitable, eternal. And around it, 400 billion stars trace their ancient paths. One of those stars is ours. One of those paths carries us. And on one small planet, orbiting one unremarkable star, you exist asking questions, seeking answers, wondering about the darkness and the light. The black hole will keep its vigil. The galaxy will keep turning. And tomorrow, the stars will still be there, waiting for you to look up and remember that you are part of this, part of the dance, part of the journey, part of the endless, beautiful mystery of existence. Rest now. The universe will be here when you wake.